Everybody should get super excited because this is the last new section in the whole class that you have to learn. Let's start by reviewing an example from last class. So in 2008, the General Social Survey participants were asked, should divorce in this country be easier or more difficult to obtain than it is now? And the results for men and women were recorded. So the possibilities for answers were easier, more difficult, and stay the same. So the null hypothesis is that gender and opinion about ease of divorce are unrelated. In these examples, you almost always write your null hypothesis and alternative hypotheses in words just because there's no sort of symbols that are obvious. And HA is that gender and opinion about ease of divorce are related. Great. Now that I taught you that little shortcut formula, you want to use it all the time. So what is the reason that you can't use the shortcut formula to find the value of this chi-squared statistic? And think about it for like 2 seconds. And the reason is that there are 2 row categories and 3 column categories. So that shortcut only applies to 2 by 2 tables. So the reason is that this is not a 2 by 2 table. So you're going to have to calculate expected values and all that junk. I know it's tedious, but that just so you know when you have to do it. So find the value of the chi-square statistic. So first we need to find our expected values. And remember the formula for that is row total times column total divided by the total, or total n. You can verify this yourself, but here are what I got for expected values. So in the male category, we've got our female category. Okay, and then there's the easier. So to find that first entry, the one that goes right here, we do 602 times 364 divided by 1272, and that gives us 172.27. In the more difficult male category, you take 602 times 609 divided by 1272, and that gets us 288.22. So that's the more difficult column. And in the same column, we take 602 times 299 divided by 1272, and that's 141.51. And at this point in time, you could check and see, does my row add up to 602? One thing that might happen is with the rounding, it might not add up exactly to 602. I think this adds up to 601.99, but it's good enough. In the female category, so for the female and easier, 364 times 670 gives us 191.73. The more difficult category will be 670 times 609 divided by 1272 is 320.78. And finally, the female stay the same category. We take 670 times 299 divided by 1272, 157.49. So there's our table of expected values. Okay, now to find the chi-square statistic, remember you do the sum of observed minus expected squared over expected. And if you want to get partial credit, you're going to have to show me your work. So for the male, easier, the observed is 165 minus 172.27 squared over 172.27 plus, next we have, just going straight across that male row, 278 minus 288.22 squared all over 288.22 plus the next one, the actual was 159 minus 141.51 squared over 141.51. And then in the female row, our first observed value was 199 minus 191.73 squared divided by 191.73 plus 331 minus 320.78 squared over 320.78. And then finally, plus 140 minus 157.49 squared over 157.49. And you really should check this yourself because half of the battle is putting this dang thing into a calculator. So when I put in a calculator, I got that this was 5.374. So you really should make sure that you can do that yourself. So next, using this chi-square statistic, we have to find the p-value. So I will talk about how to find the p-value using Excel and also how to find the p-value range. So first of all, notice that the degrees of freedom for this particular example, so the formula for that is rows minus 1 times columns minus 1. And in that calculation, you don't use the total categories. The number of rows is 2, and the number of columns is 3. So that gives us a degrees of freedom of 2. So we're in the second row of that table 8.5. So in that table 8.5, remember that your chi-squared is equal to 5.374. So look in that table, look for the ones that are closest to 5.374. And you see that you've got 5.18 and 5.99. So your p-value is in between 0.075, that's the biggest, and at the smallest it's 0.05. So it's somewhere in that range. And if you're taking a test, that's what you're going to have to tell me because you won't be given you won't be given a computer to do this. If you compute this exactly in Excel, by typing in chi-dist in your chi-square statistic, 5.374, degrees of freedom being 2, you get that the chi-squared value is 0.0681. So that's pretty close to our traditional cutoff level, but unfortunately not close enough. Okay, make a conclusion in the context of the situation. So in this case, you do not reject H naught. And the reason is, as alpha is not alpha, I guess that's quite not correct to say, as P is not less than 0.05, as P is not less than 0.05. So in this case, there is not enough evidence to conclude that there is a relationship between gender and opinion about easy getting a divorce. right, now let's move on to the new section. So testing hypotheses about one categorical variable, something called goodness of fit. So here's the motivation. Suppose you toss a 6-sided die 60 times. How many times would you expect each side to occur in these 60 tosses? So think, so if your die is fair, every side shows up with probability 1/6. So 1/6 times 60 means each side would show up about 10 times. And that would be true on average. Now, suppose you do this and you think that, you're pretty sure that this die is unfair. And what you're interested in testing is the hypothesis, the null being the die is fair, i.e. nothing is going wrong, and HA versus the die is unfair. So what you do is you toss the die 60 times and you record the number of times a particular number lands face up. Of course, you have infinite time to do this. And then you create a two-way table of expected counts. So each expected count is going to be the same. They're going to be 10, the same thing we had up there. And the observed counts are what you have from your tosses. And you're going to check, are these observed counts different enough from what you expect that you can conclude that something is actually going on. In other words, reject H0, accept HA. So then you can calculate the value of the chi-square statistic in the situation using one column as expected and one as observed. And if you've got a very large x squared, which in general means a small p-value, although that does vary a bit because this whole new degrees of freedom variable we added in, you can conclude that the die is unfair. So a chi-square goodness of fit test is used to test whether a specified set of values are the correct probabilities for the categories of the categorical variable. So another example, if you had a lottery drawing that involved randomly drawing digits between 0 and 9, you might want to analyze the observed data to confirm that the probability over the long run is 0.1 or 1/10 for each of the digits. Otherwise, you could get clever and you could analyze how often each digit shows up and you could guess the ones that appear with higher frequency. So the first thing that you have to do when you're doing this chi-square goodness of fit is you have to calculate expected values. So for example, suppose we hypothesize that 45% of a population has brown eyes, 35% have blue eyes, and 20% have an eye color that is not brown or blue, so hazel, purple, green. So suppose we select 200 people from the population, how many would we expect to have each of the following traits? So the number of people who would have brown eyes, you expect that that is NP. Remember that formula from back a few chapters ago, where N is the sample size, 200, P is 0.45. That's the expected value. So in this case, that is 90. So on average, 90 people in a sample of 200 will have brown eyes. For blue eyes, we'll take 200 times 0.35. So we'd expect 70 people in that category. And other, we take 200 times 0.2, which gives us 40 people in that category. And if you want to check that you're correct at this point in time, all those numbers should add up to 200. Next, you have to know how to find the degrees of freedom for the goodness of fit test. So the degrees of freedom is always calculated as k minus 1, where k is the number of categories for the variable of interest. So for the example of eye color, we had 3 categories of interest. The degrees of freedom is 3 minus 1, or 2. And the 6-sided die, the degrees of freedom is 6 minus 1, or 5. This actually is the same formula as df equals r minus 1 times c minus 1. And the reason is if you think about you have one category that's your observed, one that is your expected, in every table you're going to have in these cases. And then what you're going to have is category 1, so like a die, rolling a 1, rolling a 2, 3, 4, 5, 6. So this will always have 2. 2 minus 1 will always equal 1. And this is the number of categories that will be, in this case it was 6 minus 1. So the reason that they just simplify it to k minus 1 is the fact that because you only have observed minus expected as columns, you're always going to only have 2 columns. But it effectively is the same formula. All right, let's find some more expected values. So in each of the following situations, give the expected count for each of the k categories. And just for kicks, let's give the degrees of freedom as well. So this first one says in the null hypothesis that the probability of category 1 and category 2 are both 1/2. So in that case, for category 1, the expected value will be 1/2 times 100, or 50. And for category 2, also 1/2 times 100, or 50. So this could be something like tossing a die. You'd expect that the probabilities of heads and tails are equal. And because k is equal to 2, the degrees of freedom is k minus 1 or 2 minus 1 or 1. All right, in the next case, we have k equals 3, so 3 categories. So category 1's probability is 0.2. So in a sample of 1,000, we would expect to see 0.2 times 1,000 people with that trait, whatever it is, and that is 200. In category 2, probability is 0.5, so that's 0.5 times 1,000, which is 500. In category 3, probability 0.3 times 1,000, that gives us 300. And in this case, the degrees of freedom is equal to 2. All right, so let's do an actual example. So it turns out that people are actually terrible randomizers. So if I ask you to choose a random number between 1 and 10, it turns out that people disproportionately choose 7, and this is a thing. Look at how much more often 7 is chosen relative to everything else. So if we had 190 students that chose numbers between 1 and 10, there are 10 numbers there. So if they were actually choosing completely at random, what is the expected value for each integer? So since there are 10 integers, and assuming each of them is equally likely for choosing randomly, the probability of each integer is 1/10. So the expected value will be 190 tries times 1/10, or 19. So if 190 students chose between 10 numbers and they were picking randomly, we would expect about 19 people to choose each number. And you can see that that probably isn't even remotely close to true. Look at 1 was just chosen twice and 7 was chosen 56 times. So in this case, we're going to test the null hypothesis that the probability is equal to 1/10 for each number, and HA being the probability are not all 1/10. So what that's just saying is that while some probability might be 1/10 for some numbers, it is not true for all of the numbers. All right, calculate the chi-square goodness of fit test statistic. So this is the same format as the previous test statistic. It's the sum of the observed minus expected squared over expected. And the kicker here is your expected is equal to 19 for every single number, because you assume that those numbers were equally likely. So the nice thing about this is there's no need to calculate an expected value of tables. There's no row total or column total. You get that from probabilities. So in this case, so first we have the digit 1. We observed that 2 times minus an expected value of 19 squared divided by 19. We observed the number 2 9 times, so 9 minus 19 squared over 19. And keep going. We observed 3 22 times, so 22 minus 19 squared over 19. We observed 4 21 times, so 21 minus 19 squared over 19. Keep going. 5 we observed 18 times, so 18 minus 19 squared over 19, plus 23 minus 19 squared over 19, plus big old 56 minus 19 squared over 19, plus, well, 19 minus 19 squared over 19. That one's going to be 0. Okay, now we're on 9. 14 minus 19 squared over 19. And then 10, 6 minus 19 squared over 19. So you can just double check that you have 10 things there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. Okay. And that chi-squared comes out to be, holy bananas, 104.32, which is huge. And also, hopefully it should make sense that the numbers that are sort of mattering the most to this are the ones that are where the difference between the number and 19 is the largest. Like that one contributes a lot. And so does this one, and as does this one. Those are kind of like the biggest contributors and the ones that are the most different than normal. You can see that 23, 4, 5, 6, 8, and 9, they're kind of 19-ish, but the 2, the 9, the 56, and the 6 are pretty far from what you would expect. So it seems as if 7's a lot more likely to be chosen, and 1, 2, and 10, 1 in particular, is a lot less likely to be chosen. What are the degrees of freedom for this test statistic? So since we have 10 categories, the degrees of freedom is 10 minus 1, or 9. Okay, find your p-value or p-value range. So go to table A.5, look in the 9 category for degrees of freedom. The biggest value there is 27.88, which corresponds to a probability of 0.001. Because your chi-square is bigger than that, your probability is less than 0.001. If you calculate this probability in Excel, it's going to effectively give you that p is equal to 0. It isn't exactly 0, but Excel just rounds it off to 0 because it is so small. So form a conclusion and write it in the context of the situation. So we can use any level of significance that we want because the probability was effectively 0. So the idea here is that using any level of significance, the conclusion is the same. So if you want to choose alpha equals 0.05, totally fine. So at least two of the probabilities are not 1/10. So remember that HA was that the probabilities are not all 1/10, meaning that they're not all equally likely. So some of them might be, some of these numbers might be chosen with probability 1/10, just not all of them. Or in other words, you could have also said students are not likely, or students are not equally likely, to choose each of the digits. Okay, let's do one more. So one of the authors of your textbook, who probably had a lot of time, and a candy thing, purchased 4 1-pound bags of plain M&Ms at different stores in Pennsylvania to compare the color distribution to the one stated on the manufacturer's website in 2000. This person really thought that they were being shorted their blue M&Ms. So This observed results for the combined bags gives the proportions alleged by the manufacturer and the ones that this person found from their counting of the colors of M&Ms, each of the 4-pound bags. They must have made a graduate student do that. State and test the appropriate hypotheses to determine whether it is reasonable to assume that the observed colors are a random sample from a population with the manufacturer's alleged probabilities. So the steps aren't labeled, but our first step is to state the null hypothesis. So state the hypotheses. Okay. And so in this case, H naught is that the proportions are what the manufacturers claim. So the proportions are the same as the manufacturers claim. And HA is that the proportions are not the same as the manufacturer's claim, and you really are being shorted your blue M&Ms. Now, your next step is to calculate the test statistic. Now, for this one, you don't need to compute expected values because you can actually just use the probabilities. So in the chi-square calculation, you can just use the fact that the observed probability is 0.289 and the expected is 0.3, and that the red's probability is 0.19 and the alleged is 0.2. If you want to use whole numbers, you could take this 2081 and multiply it by 0.3, 0.2, 0.2, 0.1, 0.1, 0.1, and you could get numbers for each of those categories. But since we have probabilities for both of them, let's just use those. And I'm going to need a new slide because I'm out of space. So step 2, calculating chi-squared. So chi-squared will equal observed minus expected squared over expected. So for the brown probability, we observed that with probability 0.289, had an expected probability of 0.3 squared over 0.3. Plus, next we have the red category, which has probability observed of 0.19 minus expected of 0.2 squared over 0.2. On to yellow, observed 0.18, 2, expected 0.2 squared over 0.2. All right, next we have the blue, which we observed with probability 0.109 and expected probability of 0.1. Okay, then we have orange, which we observed with probability 0.116 minus 0.1 squared over 0.1. And then plus green, lastly, 0.113 minus 0.10 squared over 0.1. Is that all of them? There are 1, 2, 3, 4, 5, 6 colors. 1, 2, 3, 4, 5, 6. Yep. Okay, and I got that the chi-squared value is 0.00758. And you can already kind of see that that probably isn't going to make a very big p-value because large chi-squareds make small p-values. So find the p-value. The degrees of freedom is 6 minus 1, or 5. And in Excel, you get p equals chi-dist. You put in your chi-square statistic, 0.00758. You put in your degrees of freedom, which is 5. And you get, this is 1. Wow. So In that case, because your p-value is definitely not less than 0.5, you do not reject h naught. And step 5 is to make a conclusion in the context. So in this case, there is no evidence that the proportions are not the same as the manufacturer's claim. And that's it.